Hi friends, welcome to follow up. In this video, let's have a look at problem 2601, prime subtraction operation. So you can regard this problem as a follow-up for problem 204, count primes. So in this video, we would like to explain how to decompose this problem into smaller components and then solve the components to yield a solution for the whole problem. So here we are given a zero-indexed integer array called nums of length m. So we can perform the following operations as many times as we want. So we pick an index I that we haven't picked before, and we pick a prime p strictly less than nums I, and then subtract p from nums I. So we return true if we can make nums a strictly increasing array using the above operation, and false otherwise. So here a strictly increasing array is an array whose elements are strictly greater than its preceding elements respectively. So here we have three examples. For the first two, the returns are true, and for the last one, the returns are false. So actually the last one is very suggestive for our solution to this problem. So let's look at the first one. So in the explanation, they pick I and then minus 3, so we get 1 for the first position. So for the second position, we choose p equals 7, another prime number, so we get 2 from this index. So we have 1, 2, 6, 10. So this result is strictly increasing, so it's true. And for the second one, what we can do, for example, for the first one, so this one, it's already strictly increasing, so we don't need any operation. But if we want to subtract them, for example, for 6, we can subtract 2, or we can subtract 3, or we can subtract 5, as we like. So for example 3, so actually the return is false. And the reason is that in order to make the whole array strictly increasing, we'd like to make the last one as large as possible. Therefore, we keep 3 untouched. And then we look at 8. So in order for this one to be smaller than 3, strictly smaller, we need to decrement it at least 5. But if we decrement by 5, it's equal, so we can only subtract 7. So after we subtract 7, so we get 1, right? And here, if in order to make 5 less than 1, we need to subtract 5. But in this case, the element is 0. But in this constraint, we require the element is positive and bounded below by 1, and it's also bounded above by 1000. So that's about these examples. Actually, in between, we also touched the constraints or additional assumptions. So here I'm going to use these assumptions. First, the main information I notice we can take advantage of is that the element is bounded above by 1000. So due to this, actually we can find all the prime numbers in this range. So this is actually a easy task if we know the sieve of Eratosthenes. So this is actually also the problem for count prime in problem 204. So the plan for this video is, first we find all the primes less than 1000, and then we devise algorithm to solve this problem. For solving this algorithm, it's very natural to use binary search. So first, here let me explain the logic. So the two ingredients I'm going to use, one is sieve, right? The sieve of Eratosthenes. So this is the one part. The second part is binary search. So Um, the first part, the sieve, is just to find the prime numbers. So assume that we have the prime numbers. It's a list, right? So these are the prime numbers come into play. So this prime we are going to consider is the one starting from 2, and the upper bound is bounded. The largest one is less than 1000. And then what we are going to do is that we are going to iterate the nums from the back to the beginning. So for index I, so we start from index n-2. In other words, we start from the second to last, right? So we want to check if nums I and nums I plus 1, what's their relation? So if nums is strictly less than nums I plus 1, so we continue. So we go to I minus 1, right? So otherwise, if nums I is greater than nums I plus 1, so in this case, we need to decrement nums I by a proper prime number, right? In this case, we can compute a delta. So delta, it will be this one, delta nums I minus nums I plus 1. In other words, the prime we choose to decrement from nums I will be this, right? So let's call it P, right? P should be strictly greater than delta. The reason is that we want nums I after decrement is strictly less than nums I plus 1, right? So P should be large enough, and also P needs to be strictly less than nums. This is due to problem assumption, right? Strictly less than nums I. So nums I, right? So we want to locate such a prime. So this can be easily done using the location of such prime, if exists, is easily achieved by using a binary search. So because of the nature, so for doing binary search, it's an O log n operation. N is the number of primes involved here. So that will be our plan. So with that done, basically we first implement the sieve method, and then we use a for loop to do the binary search in between, and then the problem is automatically solved. So now let's look at the coding part. First, I'm going to write a utility function, sieve of Eratosthenes. This utility function actually has its own interest. So here we define find primes. So basically we accept an integer, right? So the integer, the return will be so I'm going to return a list. So here first we can assume that n is greater than or equal to 2. Right. So otherwise we they're not primes at all. So for this, first I'm going to initialize a list. So basically this list contains a flags. So the first two correspond to 0 and 1 would be false, and the next n-2 will correspond to true. So the index will correspond to the numbers. For example, index 1. Index 0 is corresponding to index for number 0, and the last index for nums is n-1, because here we want to find prime numbers strictly less than n, right? Find the prime numbers strictly less than n. So if we want to find less or equal, you can see replace n by n plus 1. So this is just technical detail. It's easy to be absorbed. So with that said, basically we run the for loop for the sieving method. So for p in range, so 2, and integer, so n to the power 0.5, and then here we plus 1, right? So then what we want to do is, if the current number is marked as if numbers p is a prime number, then we want to mark their multiples by false, right? Because they are not prime numbers anymore. So basically, we can start from p square. So as explained in this Wikipedia page, so you can look at the algorithm. It's actually a very elementary algorithm in number theory. So here we can iterate. So here actually we can use one line, but in order to make the idea clear, we use a for loop. So for j in range, so we start from p square, and then we end before n, and the gap will be p, right? And then we mark this numbers j to be false, right? And then we're going to return this nums. So this will contain the prime numbers. So here we can first make a test before we move forward. So let's print out find primes. So let's find primes strictly less than 10, right? So here this corresponding to 2. 2 is a prime, and 3 is a prime. There is 5 is a prime, and 7 is a prime. So, but if you want to make it more suggestive, so you can do something like this. So let's call it temp, right? And then what you are going to do is print out this one. Let's see, I flag for I flag in enumerate temp, right? So let's print it again. So you see 2 is a prime, 3 is a prime, 5 is prime, 7 is prime. In other words, the prime numbers below 10 are 2, 3, 5, 7. That's it. So with that done, basically we are done half of the job. So now let's make some preparations for the second step. So second step basically is binary search driven logic. What we want to do first, let's find primes or not, right? So here basically we call this find primes. So the nums, so basically I can use see 1001, right? 1001. So basically we find prime numbers strictly less than 1001. So actually 1000 is not prime, so it doesn't matter. You can write 1000 here. And then let's find the primes. So the primes will be, so let me use a list comprehension. So I for I flag or boolean. So in enumerate primes or not, right? So if the flag is true, it's a prime number. So now that we know these prime numbers, and then we can write the problem logic. First, for convenience, let's get the number of primes, and also n, the length of this nums. So this is just for iteration purpose, right? For iteration convenience. And then what we're going to do, so let's see, binary search usage. So here for I, so we're going to iterate from backwards, so start from n minus 2, then ending at 0. The increment will be -1. In other words, we decrease in the index. And then we check if nums I is strictly less than nums I plus 1, right? So we do nothing. This also implicitly saying that for the last number in the list nums, we don't touch it, because we want to make it or keep it as large as possible, right? So we continue. Otherwise, so first we check delta. So that is nums I minus nums I plus 1. So as we mentioned, in order to decrement the current nums I using a prime, we need the prime p to be larger than this delta and smaller than this nums I, right? So let's do a check. So here IDX, so I'm going to use the bisect module in Python and bisect right. So the search iterable is primes, and the target will be data. So in other words, if we want to insert data in this primes, which is sorted, so what's the index, right? So here, if idx equals m, so it means that all the prime numbers are less than or equal to the delta. So in this case, we just need to return false, right? Because we want to decrement by a prime number that is strictly larger than delta. So this is the one case. So now let's look at another case. So in other words, the idx is less than m. So in other words, we can insert this delta in between. First, if prime idx, so at this one. So here we are using bisector right. In other words, right to this idx, all the prime numbers are strictly larger than the delta, right? So if this number is, say, prime idx is larger or equal than nums I, right? So we are going to return false because we couldn't find this number, because we require this number to be at least strictly larger than delta and strictly less than nums I. So if it's no less than nums I, so we return false. Otherwise, so what we do nums I decrement by this prime number, that is nums, not nums, primes at idx, right? So after this, so basically what we do, if we haven't got anything returned, so we just need to return true. In other words, we can make this list to be strictly increasing. So with that done, basically we finished the coding part. So before we make any comments, let's first do a test. Yeah, it passes the last example we tested. So now let's look at the generic case. Yeah, it passes all the generic cases fast. So now I guess in order to digest this one more clearly, so we can print out the final state of this nums. So now let's do this. So we can print out this nums after we do the subtraction. So let's test for this example. Right. So after we subtract, so here 6 is less than 10. We didn't do any subtraction. So 9 is greater than 6. So we need to subtract at least 3. But 3 is larger than 3. So the prime we choose is 5. So after we subtract 5, we get 4. So once we have 4, so 4 equals 4, right? So we need to pick a smaller prime, that is 2. So 4 minus 2 is 2. We get this one. Now let's also look at the second example. So it will print out itself, right? Yeah, this is the original input. So now let's look at the last one. So I guess for the last one, there's nothing output. So because it's already returned. So it returned false because as we look at 8. So 8 is greater than 3 by 5. So we need to at least to decrement something greater than 5. So 7 is the 1. So we get 1, 3, and then we cannot continue. So it does not. So here the program does not print the state. So now let's comment this out. So with that done, basically that's about it for this specific problem. In this video, so we split the logic or the problem into two parts or two ingredients. So first one is we use sieve, specifically the sieve of Eratosthenes, to get the prime numbers below 1000. And then we use binary search, and we do the iteration reversely, and we do this prime operation specifically here in a greedy fashion, and finally we make the returns. So with that done, basically that's about it. And if you find this explanation is of use, so you can follow me up in my channel or the corresponding playlist. Thank you.